of heat transfer, right? Different possible modes, conduction, convection, radiation, and also we have seen combination or combined modes of heat transfer which exist in practice. In fact, we have considered only conduction and convection combination, right? In practical cases, all three will exist in most of the cases. So that will become little more complex, which is not in our scope at undergraduate level. So now, why do we need to understand the concepts of the heat transfer mechanism? This is theory. All that we have seen is theory. It is a mathematical formulation and some calculation. But where are its applications actually? The purpose of we studying this is somewhere it is useful. See, for example, what is the use? Take the simplest application. You have sun heat, solar heat. It's available, source is available, and you have an application where you need to heat the water. So water is at a certain temperature and you want to heat it. So now the heat of the sun shall be utilized to raise the temperature of the water. That means you must transfer the heat of the sun to the water. So what all we talked about so far is, if you know there is some body and there is source and sink, how much heat is transferred, what is the temperature of the sun, what is the temperature of the water, what is the mode of heat transfer, and then what is the heat transfer rate under given conditions. That's what we discussed. Now, in order to actually affect this heat transfer process, affect the heat exchange process rather, you need to have some equipment, right? So only then that heat exchange is possible. Another example, what do you use? Solar water heaters. There will be a setup, right? On the roof of a building you have some collector where it collects, and then there will be pipes through which the water will flow, and then that receives the heat. So that arrangement is a heat exchanger, where water is flowing while receiving the heat, heat from the sun. That is the heat exchanger. Heat exchanger is a device which is used to make that exchange of heat between the two mediums or between the two matters, let us say, possible. Okay. So another simple application, you take electric geyser, one kind of heat exchanger. Or let's say hot gases are going out, which are coming through tailpipe of IC engine. Hot gases are coming out, and you can use that heat to any purpose where heat is to be consumed. Again, let's say to heat the water. So therefore, gas is the source. Hot gas coming through the tailgate is the source, and cold water, which is available at your disposal, is the sink. Now, if you can bring them together through some equipment, it is possible that you can transfer the heat from the hot gases to the cold fluid. So that equipment which affects this heat exchange between two fluids or between a solid and fluid or whatever it is, right? So that is called a heat exchanger. In most commonly used cases, there will be a solid surface, right, which is used to affect the heat to be transferred from hot fluid to cold fluid, right? So now, there are different types of heat exchangers, right? You observe this. Inside there is one passage, one path, let's say inner pipe, and around this there is another pipe. It's like you can imagine this as a refill in your pen, and outside also there is space, right, between the refill and the outer tube of the pipe. So through one channel, one fluid is going, that would be hot or cold, and through the other channel, another fluid is going. If it is hot, this is cold. If it is cold, this is hot. So while it is traveling across, right, so there will be a heat transfer between the hot and cold fluids through the surface, which is common to both the fluids, right? The common surface area. There is no heat transfer here, right? There is no heat transfer here. Are you following? What is the surface that is common to both the fluids? This surface. Suppose if you see in the side view, this is one circle. So this is having certain thickness. Now here, since both the fluids are flowing in the same direction, we call it as parallel flow heat exchanger. Now you see the other case. Same arrangement. It's a concentric tube. Concentric tube is tube in tube. So here, one fluid is moving in one direction, while the other fluid is moving in opposite direction. So this is called counter flow. Parallel flow and counter flow. Right? So these are the simplest possible configurations. And it is said here that counter flow heat exchanger will have better effectiveness or performance, which we will see later when you solve some numerical problems. Now, this is a pictorial representation. So, one fluid, say cold fluid is moving through inner tube, and as it moves, it picks up heat from the hot fluid which is circulated around that, and then its temperature increases. Temperature of the cold fluid increases. That's why it is mentioned as warm fluid here, out. And now the hot fluid is entering here. Because it loses its heat to the cold fluid, its temperature reduces. Right? So now, in terms of temperature profile, you please observe this carefully. Temperature is taken on y-axis, and then the length of the exchanger is taken on x-axis. Now, as the hot fluid is moving, see, this is end 1 and this is end 2. So this is end 1 and this is end 2. This is a schematic diagram of this, not two-dimensional view of this. Right? This is represented, say, in front view. One fluid is flowing here, another fluid is. See, this can be hot, can be here, cold, can be here. It doesn't matter. Right? So just line diagram of this. Now, the distance from this point to this point is nothing but the length of the heat exchanger. You just project it up. That's how you get it. These two lines. So this is x is equal to 0, that is the length. This is x is equal to L. Okay. Now, hot fluid as it moves from this point to this point, it loses its temperature. So its temperature is dropping gradually down. So it is 0 to T on the scale. Y-axis represents. Now the cold fluid, it is also moving in the same direction, and as it moves through the length, its temperature increases gradually. So this is decreasing temperature of hot fluid, and this is increasing temperature of the cold fluid. Now, if you take the counter flow, right, where both the fluids are moving in opposite direction to one another. So now, hot fluid is moving in positive x direction and cold fluid is in negative direction, whatever it is. Now, as it moves from this point to this point, hot fluid, it is losing its heat. So therefore, its temperature is dropping. Now, cold fluid is entering here. Cold fluid is entering at the end where hot fluid is leaving. So it starts here. So as it moves in the opposite direction, it absorbs the heat from the hot fluid. Therefore, its temperature increases. Right? Now, another type of heat exchanger, cross flow heat exchanger. So there, either in the same direction or in the opposite direction, but here they are perpendicular to one another. You see this, right? So there are some tubes here. One fluid is flowing in tubes, and these are the plates which we call them as fins, right? So it may give stability also to keep all these pipes together at certain space. So now one fluid is flowing perpendicular to this through the gaps between successive plates. These plates are fins. Why you have added fins here? To increase the heat transfer area. Now the purpose of fin is to increase the heat transfer area, thereby increasing the heat transfer rate by convection. HA delta V. A increases, heat transfer rate increases. Now, what's the difference between these two? Right? Both look like the same, but the difference here is, see here, the fluid fluid which is flowing in the tube and the fluid which is flowing outside, they are not mixed, right? They are unmixed. Whereas here, the one fluid which is flowing through the tubes is not mixed. Each layer of fluid is moving in its own path. Whereas the fluid which is moving in perpendicular direction, it is mixed. It does not have any separate paths. It's like when the people are walking, right, in certain paths here, Republic Day or Independence Day, people are walking in the defined path, different lanes you can see, or vehicles are passing in different lanes. If there are that's similar to what is there through the pipes. But when no such lines are there, it's wide open. You can go this way, right, zigzag, whatever, or across the road. It's not defined. So it is mixed, right? And the same diagram shown in with some better clarity, right? So here, if you see the observer, there is transverse direction, whereas where here it is perpendicular. Now another category of heat exchangers is shell and tube. Shell is a big container, right? Tubes can be placed inside the shell. Just imagine the air compressor that you see to inflate your tires. So that is a shell. So inside that there are pipes placed like this. So some fluid can enter through the tubes like this. So it is entering here and then leaving here. Tube inlet and tube outlet. Now another fluid is entering through the shell, right? And then it moves, here and there and then exists here. These vertical lines in black shade of color are known as baffles. And the purpose of those baffles is to create some disturbance in the flow such that it reduces the speed of the fluid so that it can wet the surface as much as possible. See, it is something like that. If water is flowing in the agriculture field, right? Will you just suppose for irrigation purpose, I am saying there is a crop and then you want to water it. Will you allow it just to pass it from one end to another end? Or what do you do? Anybody having experience in agriculture? Those of you sitting here, no? Nothing. That's why you are not writing any notebooks and all, right? None of you have the experience? Really? You have, right? So he knows, probably. Did you ever go to fields? Huh? No. So they know. So what do? While water is flowing, they will keep obstructions so that the water flows in lateral direction and wets as many, plants as possible. If it is allowed to go just in one path, it can wet only, certain lines of plants. Right? So therefore, our idea is to cover the area. See, otherwise what will happen if there are no baffles? By gravity, it settles down to the bottommost position. And then with pressure, it just, moves and then exits. So what about the pipes that are in the upper place? So it will not be touched by the other fluid. So there is no heat transfer. That's the reason why. So the flow is created in such a way that it covers the entire surface. So those objects are called baffles. So here it is called one shell pass and one tube pass. What does it really mean? See, the fluid that is entering through the shell is moving through the entire structure only once, through the entire length. Right? It is entering at one place and leaving at the other end. At one end it is entering and leaving at the other end. So it is completing one shell pass, covering one length of the shell. And similarly, what is happening to tube? It is also same, right? One tube pass, entering at one end and then leaving at the other end. So therefore, one shell and one tube. Now see, how is this? How many shell passes here? One or two? Tell me. One or two? One shell. So it is entering here and leaving, entering at one end and leaving at the other end. How many tube passes are there? Huh? One or two? entire length once and again returning. Like you are going to your village and come back. How many trips are there? Two trips. If you just go and then end up there, then it's just one trip. It's like how many times you are traveling between you and this your place and this place, right? Something like this. So it's going and then coming back. So there are two tube passes. One shell pass and two tube passes. Now you tell me what is this? How many shell passes? Shell.
Two, sir.
One or two? Two. So it is entering here, blue color shell fluid. Entering here, reaching the other end. Again, starting from there and reaching the other end. So two times it is moving in the shell. So two shell. How many tube?
Four.
Four. Right? So this is how it is. Two shell passes and four tube passes. Now, these are some practically used commercial heat exchangers, right? So those are just pictorial representation for understanding, but this is the actual picture. See, there are tubes inside, and this is the shell. If you observe carefully, there is, this cross section is divided into two halves, upper portion and bottom. That means in one direction it goes and then comes back. So there are two tube passes. The shell is entering somewhere here and then leaving at the other place, right? Now exploded, right? Shown different parts, how they are assembled. And then see here again. So this entire tube bag is just in one direction. It's not unlike in the previous case. There is no division here. So enters at one end and leaves at the other end. Tube fluid and shell fluid. And this is also another type. See, there is a tube, right? And also outside here it can enter and move around this. Right? There is a cell. See, one example here. If you observe in your refrigerator, you will find this kind of arrangement. Right? So refrigerant is flowing inside and the air is flowing outside. That is another example. Now, another category of heat exchangers, compact heat exchangers. Compact means it's a small. See, there will be certain applications where larger amounts of or larger quantities of heat is to be transferred per unit volume, right? In as much less time as possible. For example, your mobile phones. Lot of heat is generated, inside. But then the space that you have is very limited for the heat to transfer. So still, heat transfer has to take place. Otherwise, the temperature or the heat builds up inside, which will lead to the rise in temperature. And any circuits or chips are sensitive to temperature. That material that is used for circuits is very sensitive to temperature. Beyond certain point, it melts. So therefore, you have to keep under certain temperature. That's the reason why computers are recommended to be placed in air conditioned environment. The reason is that, right, to keep it under some controlled temperature. Okay. So now the compact exchanger is nothing but you have larger surface area per given volume, right? So because volume is limited, the size of the object is limited. So within that, you should see that A in HA delta is maximized. So the simplest possible definition for this is that the heat exchangers which will provide larger heat transfer areas per given volume. So these are the compact heat exchangers in different shapes and sizes as you see here. So these are the types of the heat exchangers. There is a surface, solid surface, which is separating the two fluids. So therefore, what are the different modes of heat transfer that are here? Convection on hot fluid side, convection on cold fluid side, and conduction within that wall, whether it is a plane wall or cylindrical wall or spherical wall. So there are three resistances, two convective and one conduction. So in conduction, the coefficient is K, right? And in convection, the coefficient is H. But when both conduction and convection are present concurrently, then you must have some coefficient which represents both. That is what is known as overall heat transfer coefficient. This is convective heat transfer coefficient. This can be called accordingly conductive heat transfer coefficient. Now this is overall heat transfer coefficient which represents both of these. So how do you get a mathematical expression for this? Right? See, for example, if you take a plane wall, right? Plane wall like this, right? So this is the plane wall which is separating two fluids, right? Which is separating, say, hot fluid here and cold fluid on the other side. So there is some temperature of hot fluid and it drops here and then further through the conduction and then again some the temperatures. So our standard notation is we consider this as T1, T2, T infinity 1, T infinity 2. Is it what we note it down? In our convention any different? Right. So this is what it is. So now, what is the heat transfer equation that you write here? Heat transfer across the wall, Q is equal to overall temperature difference, right? T infinity 1 minus T infinity 2, right? Divided by, what is the resistance of the hot fluid? Convective resistance 1 by H1 into A. Because this is a plane wall, area on both the sides is same. Otherwise, I could have written this as H1 A1. Now I am assuming heat transfer coefficient of hot fluid is H1, heat transfer coefficient of cold fluid is H2, and thermal conductivity of the surface that is separating them is K plus L by Ka. What is L? L is the thickness of the wall. Thickness of the wall. L by K plus 1 by H2 into A. So in a way this is delta T overall divided by sum of resistance. Now U is defined in such a way that, let us say this is the equation 1. U is defined in such a way that U is equal to U A delta T overall. See, if it is simply convection, we would have written it as HA delta T. If it is conduction, Ka delta T by L. Right? Now U is taking care of both. Now this can be written as Q is equal to delta T overall divided by, how can you write this? 1 by UA. Now let's say this is equation 2. So by comparing equations 1 and 2, comparing equations 1 and 2, what do you get? 1 by, numerator is same, right, for both. Are you getting me? Sum of these resistances. This is the sum of resistances. So numerator is same for both. So therefore denominators are equal. Are you getting me? Q is equal to delta T by, otherwise you write one more time completely. Entire equation. 1 by H1A plus L by Ka plus 1 by H2A. This is equation number 1. Right? And now I am defining U as Q is equal to UA delta T. This is my overall heat transfer coefficient. And I am rewriting this as. Now I am asking you to compare equation 1 and equation 2. What do you get? 1 by UA is equal to 1 by H1A plus L by AA plus 1 by H2. A is common throughout. So therefore you can write 1 by U is equal to 1 by H1 plus
1 by K.
L by K, not 1 but L length, plus 1 by H2. Right? So U has the same unit as H. Right? Because Q is equal to HA delta T is convection heat transfer, Newton's law. So now U will have the same unit as H. So 1 by U is equal to this. This is for what? For a plane wall. For a plane wall. Suppose if it is not a plane wall, right? If it is, say, some cylindrical wall. So this is the structure that I have taken. Right? So for this structure, this is the thermal network diagram, and of course here he has taken U C for cold fluid, H for hot fluid. We just leave this, right? So you may please note this down. Overall heat transfer coefficient, comma, denoted by capital U, is used to cover the effects of conductive coefficient K, conductive heat transfer coefficient K, and convective heat transfer coefficient H. The cases of combined modes of